an irresistible force such as you meets an old immovable object like...
In this lesson, our primary focus is to try to answer the question, what is a function? But before we do that, and to make it easier, first we're going to discuss what is a relation. A relation is a matching or pairing of two sets. We could use here as an example. An example of a relation would be the matching of a street with the people who live on the street. A relation that maps a street name on a bus route with students who live on that street can be defined in a set of ordered pairs. For instance, Jared and Jill both live on Sycamore. Ken, Tom, they live on Oak. And Harry, Phyllis, and Nadine all live on Maple. So a relation is a mapping of each element of one set, we're going to call it a domain, that matches it to an element in the second set that we're going to call its range. With that in mind, now we can answer the question, what is a function? A function is going to be a relation in which each element of the domain is mapped to one and only one member of the range. So that's not too difficult. Here's an example. Let's say we have a function which we're going to call function f. It consists of the name Alice. Alice is 17. Barbara's 14. Chris is 16, Dennis is 19, Enid is 15. So the domain in this case is simply Alice, Barbara, Chris, Dennis, and Enid. And the range is 14, 15, 16, 17, and 19. Another way we could present this information is a mapping diagram, where our domain is on the left and our range is on the right. The way we'll use a mapping diagram is to draw arrows connecting each element of the domain to its corresponding element in the range. Now, except for the new vocabulary, that's still not too difficult. But your big question will be figuring out what's a function and what's not. So let me show you a pretty obvious example of something that's not a function. Let's say we work this a little differently. What if we redrew it this way and said that Barbara was both 14 and 16. This is not an example of a function. I like to use this example often because it's ridiculous and therefore memorable. I mean, Barbara couldn't be 14 and 16. We're going to apply this a lot when we try to figure out if something's a function or not, and I'd like you to do that now. Let's look at the example we used at the beginning of this lesson. I'd like you to match the street names in the domain to the student names in the range. I need you to decide if this is a function or not. Please click pause now until you make your decision. So, putting aside the question of how good is your memory, let's get back to the essential question. Is this a function? You can see that the street names on the left map to more than one student name on the right. Try to remember our age example. In other words, the names on the left have more than one age. This is not an example of a function. Now I need you to apply what you've learned so far to a number of different examples. Take your time and decide which of these relations is a function. Click pause now until you're done. Okay, let's look at them one at a time. So in A, it looks like 7 maps to 4 and 1 maps to 4, and if you remember, that's okay. Two different people can have the same age. In B, if we were to write the domain and range as a set of ordered pairs, 1 maps to 1, and 2 maps to 3, and 4 maps to 2, and 7 maps to 3. And to really use that example, so none of our students have this 2 different ages. In C, that's a little more difficult to see, but think of 2 ordered pairs that would work. Let me give you an example. How about 4, 2 would work, and 4, -2 would work. Unfortunately, that means one of our students has 2 different ages, so C doesn't look like it's going to be a function. Let's look at D. D, we have 1 mapping to 2, and we have 1 also mapping to 4. So we have 2 examples. We have an example of a student who has 2 different ages. So that fails our test also. So it looks like if we're going to figure out A, B, C, or D, which ones are the functions, it looks like A and B are both functions, but C and D, unfortunately, are relations, but they're not functions. In problems where you're given a graph, these are going to be the easiest of all. We're going to use what's called the vertical line test. You notice on the left, every vertical line straight up and down you draw only hits the graph once. But on the right, well, you can draw lots of vertical lines and they hit the graph twice. So let's try to apply this to several examples. Pause the tape now and use the vertical line test to decide which of these are functions and which of them are not. So using the vertical line test, 1 looks like a function, 2 unfortunately fails because we can hit the graph twice, 3 is a function because we only hit it once each time, and 4 is a function because we only hit it once each time. So the next essential question is, what is the domain of a function? Once you've determined if something's a function or not, you need to be able to tell what the domain is. And I'd like to suggest, algebraically, determining the domain of a function really comes down to understanding what x values cannot be used. Here we have a graph of the function 1 over x. You can see how the function keeps getting closer and closer to the axes, but never crosses them. And algebraically, we can figure out why. If x was equal to 0, then we have division by 0, and that's undefined. So that's not allowed. So the domain of this function is going to be any number at all. And we write it this way. X is defined as any number except x cannot equal 0. So now that we've determined the domain, we can determine the range. The range is any number except y is never equal to 0. So expanding on this example, any function you find that has a fraction in it, you have to look for what will make the denominator equal to 0. That's how you'll determine the domain. In this example, I have a function that has a square root in it. So square roots work except when we try to take the square root of a negative number. So the domain of this function would be any number where x plus 1 is greater than or equal to 0. Subtracting 1 from both sides, I'm going to find that x, the domain, can be any number, as long as it's greater than or equal to a negative 1. You can see from the graph that this function begins at negative 1 and takes off to the right. Therefore, the domain of this function is going to be any value of x. Any value of x, that is, as long as x is greater than or equal to a -1. Given this, and you can tell from the graph itself, the range, or the y values, could be anything as long as they're equal to or greater than 0. So those are the two examples I'd like you to watch out for: square roots and fractions. Square roots of negative numbers and division by 0. And that's it. Now you should be able to determine whether or not a relation is a function, and given it's a function, determine its domain and its range. Thank you for your time and attention.
As sure as we live, something really got to